Going on now to the last topic of Chapter 3, Section 6 is on function. Now, function is something that's going to be very important in future math courses, so it's sort of an important thing to know. Now, some terms related are the word itself, relation, domain, range, and the word function. Now, again, as we do these tapes, what I'm trying to do is show you a strategy and sort of make it easier for you, if I can. And then there's also the textbook as your basic first reference. So we're very familiar with this already now. This is the ordered pair, that the order is significant, and we start with an X and a Y. Now we know if we plot these on a graph, this will be your X units, this would be your Y units. This gives you a specific point, and therefore these two letters are connected. That is, they are a relation. And that's what the word relation refers to, that things are somehow connected. Now when we get to the word domain, domain and range, these go together. Now notice this starts with a D and this starts with an R. And actually they refer to the X and Y elements of the ordered pair. So if you put these alphabetically, domain, range, the D relates to the X element and the range relates to the Y element of your ordered pair. And then a very short definition of what function is. Function occurs, or something is a function, if the X element in your series of relations are only used once. If the X element is used more than once, it is not a function. And more about that as we go on. Now for our first example, this is rather straightforward. They want us to find the domain and range of these relations. So it's rather easy. I suggest you set it up as domain equals, and this is going to be in roster form. And you list the 0, the X elements. In fact, I could put underlines under them. And then we have a 3. And we have a -1. And we would have another 3 in there, but the rule is if the element that you're looking for is repeated, you don't write it more than the once. So this would be the domain. Now for range, we have a 2, a 3, a 0, and a -2. Now even though it doesn't ask at this state, is this relation a function? And we could kind of stick that in here as well. And the answer is the X element used more than once in this relation? And we said yes, the 3's are used more than once. So in terms of a function, this is no, it's not a function. To cut down writing on the board a little bit, instead of writing out all of those ordered pairs, you can look at the book and you'll see some as examples and quiz me's. In example A, that relation, there were no repeats of the X element, so A is a function. In example B, we saw as we went through the O, which was an X element, was used twice. So this is not a function. In example 3, they give you a fancy graph. I've just sketched it. Is this a function? this graph where we've plotted these points? And the answer is, notice, this would be like a -4, a -3, a -1, a +2. So are the x elements of these ordered pairs repeated? And the answer is no. So yes, this is a function. Now as we look at example B, we have this element, which is like a -4. But here, notice that in listing the coordinates of these points, it would be a 2, and let's say a 2, and this would be a 2 and a 4 up there. So the x element would be repeated in this example. So this is not a function. As we go into example 4, this is something very useful. It's called the vertical line test. This red line, it stands for a very thin vertical red line. Now as we move this vertical red line over the face of the graph, this, remember, is positive slope. Does this represent a function? And the way the vertical line test is, if the vertical line only intercepts in one place as it goes across, which is what is happening here, we say this passes the vertical line test, and yes, this is a function. Now this is an upside down parabola, and again we're bringing this vertical line over the face of this graph. Does it intersect in only one place? Think about it for a moment and try to imagine it, a vertical line passing over the graph. And the answer is only intersects in one place, so this is a function. Now how about this line, which is like y equals -3? Is this graph a function? And again, it's this vertical line traveling over the face. And again, it only intersects in one place, so yes. Now when we get to the circle, we notice that the line will be intersected there and not in just one place. So a circle is not a function. Now some other ones while we're here. How about, let's say here this is x equals 2. Is this graph a function? Does it pass the vertical line test? And the answer is no. Because once it gets over that line, there's lots of places, an infinite number of places, so no. And then another quick one, how about a sideward parabola? Again, does it pass the vertical line test? And the answer is no. So this is not a function. In example 5, they're giving us these 4 equations, and they're saying, do these equations represent a function? Well, here is y equals x, which is this graph. So we did that one. That would be yes. Y equals 2x plus 1, you might recall, is slope-intercept, and that's a function. Y equals 2, that's a function. Now x equals -1, we had said it does not pass the vertical line test. So we have 3 yes and 1 no. Example 6 is too difficult to illustrate on the board and would take up too much time. But here, these are months here, January, February to December. And these are times over here. So they're asking you for sunrise or sunset, something like that. And they'll say, let's say in August, what is the time of sunset? Well, you're theoretically going to make something like this. And this will be your, in a sense, your x coordinate. And whatever is here will be the corresponding y coordinate. So they're going to ask you to be able to read, in a sense, that graph, and from the graph, pick out some information. Okay, a little summary of what is in the next few pages. They're going to introduce what is called function notation. So what is function notation? Well, it looks something like this, where you're saying f of x is 2x plus 1. You might also say g of x equals x squared plus 2, or h of x equals something. So this is function notation, where you have some letter, and then usually x in a parenthesis. Now, normally we think of parenthesis to indicate multiplication, but this doesn't indicate multiplication. What they're going to do here is go like this. They'll say f of 2, f of 3, f of 0, and basically what they want you to do is put in this value as your x, and then something comes out of it. So my strong suggestion, when you are asked to do something like this, is to make a t-chart where your x value goes there. This is from what we just had in earlier lessons. And then what will come here will be your f of x. And this is like super critical. Your f of x, we can always think of that as if it were a y in our ordered pair. This is considered our y value. It's just another way of writing y in a function notation format. So what do you do here? Well, you take your 2, your 3, and your 0, and put it in to your statement, so to speak. So if x is 2, what will y be? Well, 2 times 2 is 4, plus 1 is 5. 2 times 3 is 6, plus 1 is 7. 2 times 0 is 0, plus 1 is 1. So, when x is 2, f of x is 5. Remember, this is another way of thinking of y. And one of the other concepts they introduce is this idea of input of something yields output. Well, your input, interestingly, is your independent variable. And your output is a dependent variable. Here, this is independent. But once you put something in here, then your output is sort of dependent on what was put in. So what is your independent variable here? Well, it's your x values. X values are independent. That is your input. Your x is your input into the system. This equation, by the way, is what that arrow stands for, or that expression. because that's what you're doing to give you your output, which is a dependent variable on what you put in your independent. And that's basically the start. Now we'll get to some examples. So, for example 7, they give us the g of x, again in function notation, is this. And then they have these as your values of x. A 2, a -2, and a 0. So you're to put that in to see what comes out. So here, if x is 2, x squared is 4, 4 minus 3 is 1. If x is a -2, -2 times -2 is still a positive 4, minus 3 is 1. And if x is 0, 0, that would be a -3. So again, I strongly advise that when you're asked to do function and to generate input to output, you use a T-chart. That's what you are already familiar with. For example 8, they're asking us to find the domain. Now, if you remember, we said domain were the x elements, and x's in a graph, the x-axis is this horizontal line. So they're asking us to find the domain of this function. Well, a little background is, can we ever have a number in which our denominator is 0? And the answer is no. We said that this was undefined. So can you see here that in defining this particular x, what values can we have for that x? Well, it would be any real number but x cannot equal 0. And this is sort of in what we call set builder notation. But they want us to give the answer in interval notation. So in interval notation, x can be on this number line any number, but it cannot be 0. So how would we indicate that? Well, your textbook gives you this, and I'm going to tell you how to do it right now. That this is coming from -infinity out here, going up to 0, but not including 0. And then on the other side, it starts at 0 and goes to positive infinity. Now, how do we link these together? Well, in algebra we have this special sign, which is a union sign, which is sort of a U. So this is interval notation. This is set builder notation. And we'll give you a few more examples as we go on. Oh, we got to do this one too. All right, for letter B, are there any limitations? Can x be a 0 there? Sure. Since this is all in the denominator and our, I should say numerator, and our denominator is 1, there are no limitations. So when there are no limitations and we indicate the whole number line, we say it's from -infinity to positive infinity. This is all real numbers. So a lot of math theory in there, but let's go on. For this example, 9a on page 233, we're asked to, again, from this graph, define the domain. Now, notice our domain refers to x units. So if we project this up to this line, and this down to this line, these are the x units in our domain. So it starts here at -3, and -3 is included, and it goes to 4, and 4 is included. Now for our range, again, we're reflecting it over, it goes to there. Our range are y units, and it goes up to there. So that's what we want. We want to reflect that to the y-axis, and that's going to start at -1 and go up to 1, 2, 3, 4, 5. You can actually sort of pick it out from our ordered pair. Now for a parabola in letter B, notice that this continues and eventually goes to -infinity out there in terms of our x units, and positive infinity there. And infinity is always written with a parenthesis. And our range now, I believe I have the 3 is negative there. There we go. So it starts, again, projecting it to your x-axis. It starts at a -3 and then continues up to positive infinity. Now, this finishes our work on chapter 3. But you know, if you look carefully at your textbook that you have online, there are extra exercises. There's also chapter tests that you can look at. There's chapter summaries, lots of good stuff. And hopefully you are getting ready now for your chapter 3 test. Do the practice, the quiz-me's, and get mastery, and then your tests. So good luck. We'll be starting chapter 4 next.